So in this session, we'll be discussing week 5. Okay. So, so let me start sharing. We'll discuss the concepts of week 5, okay, and after that we'll look at the activity questions. If the time permits, then we'll also look at the sorry. If the time permits, then we'll also look at the practice assignment questions. All right. Is that fine?
Yes, sir.
Okay.
Yes, sir. Sure.
Yeah. So sorry we were not able to conduct the session yesterday because one of our course instructor one of our course instructor he was not prepared, so we were not able to do it yesterday. Check the live stream if that is working. Let me just check it.
Even week 4 videos are not uploaded sessions and not uploaded till now, sir.
Oh,
Both
what
both the
happened?
both the sessions were taken by you only, sir,
Yeah,
and
yeah, 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 yeah.
those
So
sessions
what
have
happened
not been
is
uploaded. Yes.
correct. So for unfortunately for one session, since we did not record it, okay, we were not even able to upload it later, and because the live stream failed, we were not able to upload it. But sorry. But for the second session, we do have a recording. Okay, we do have a Gmeet recording, so that can be uploaded to YouTube. Okay, that will be taken care by the support team. Okay, so they will be taking care. Okay, the portal team. Okay, they'll be taking care of it, and we'll be uploading it soon. Okay, so just give us a moment and give us like by the end of today or tomorrow. Okay, we'll upload it. Okay, so one second, we delete this. Okay. So what we'll do is we just like we have done previously. Okay, we look at the slides of it. Okay, and then we'll try to understand the concepts. Okay, if you have any doubts, you can just stop me at any point, and then we'll discuss there.
YouTube streaming is not happening.
Yeah, there was a problem with this YouTube streaming. It was happening across courses. Okay, not just with MLF. So yeah, anyway, we are doing this local recording, so we can upload this later. Okay, you do not have to worry about this. It's just that it could be delayed, the uploading, but it will be done. Okay. Okay. So let us get on to this. So in week 5, what was introduced was this complex. Okay. The complex numbers and then the complex numbers. Okay. The the things associated with this complex matrices. Okay. So first we look at this complex numbers. Okay, anything that has this imaginary number, right, I, which is the square root of -1. Okay, so that is called as this complex number. And then the general way the complex number exists is this a plus ib. Okay, a plus ib where a is the imaginary part and b is the sorry a is the real part and b is the imaginary part. Okay, so a plus ib together forms this complex number. Okay, so how do you represent a complex number? You can actually represent a complex number by using a point, using a point in a two-dimensional plane. Okay, in a two-dimensional plane, you can represent a complex number. Okay, so the way you do that is you represent the a in x-axis. Okay, so the x-axis will represent the real value a, and then the y-axis it will represent the imaginary value b. Okay, so together this a plus ib, it will be representing this complex number. Okay, so
And then, sir, then what?
yeah, hello, I'm not able to hear you.
Sir, say for example, 3 plus 5i is there.
Yeah,
So you are saying that 3 will be on x-axis and 5 will be on y-axis, right?
correct. So the point will be 3 comma 5.
So what about I part, sir? I part?
Yeah, so that will be there in the imaginary. So the 3 comma 5, right? 3 comma
Yeah.
5 point. Okay, in a 2D plane that represents this complex number. Okay.
Okay.
All right. So here,
Okay.
even here, we could see here a plus ib. So basically this point, right? It will extend. I mean, this vector. if we start from this origin, it will be extending up to a comma b. Okay, so where this a will be this real part, and then this b will be the imaginary part. Okay, and this theta, right? This theta is nothing but this tan theta. Okay, you could consider that as a slope or whatever. That's going to be equals to b by a. Okay, and then this length of this, right?
So,
I
sir,
mean,
this theta is with x-axis, right?
yeah. So this theta with respect to x-axis. So if we just want to draw this, okay. So let's say we have the number a plus ib, okay, and we have this is the real, this is the imaginary part, the y-axis, and this number is this a comma b, okay. So okay. So this is the angle theta, okay, which it makes. So this is b, right, and this is a, right. So this tan theta is going to be equals to b by a, okay. So and what we say is, okay, and then this length, now this length is going to be equals to what the hypotenuse, right? Length r, okay, it is going to be equals to a square plus b square, okay. So this r you could say it as the length of the complex number, okay. So we have here r equals to a square plus b square, and then this tan theta equals to b by a. So the other way of representing it using this theta, okay, theta that is this angle with which it makes with the horizontal or the real axis, and then the length of that length of the complex number, right? So using this, you can represent a plus ib as a plus ib can also be represented as r e power I theta. Okay. So what do we know about r e power I theta? E power I theta. E power I theta is nothing but sorry, it's going to be cos theta plus I sin theta, right? Am I correct? Here, cos
Yes, sir.
I sin theta, right? Okay.
Which one, sir? Which one?
E power I theta. E power I theta, it's going to be equals to cos theta plus I sin theta, right? So r e power I theta, it's going to be r into cos theta plus I sin theta, and we know that r equals to what? Square root of a plus a square plus b square.
Sir, how we are getting, can you derive?
Oh, the c power I theta equals to cos theta plus I sin theta. You want me to derive that part?
Yes, sir.
Okay, so I am not going to get into that because that's the standard one. Okay, and then that's going to take some time. Okay, so for now, what you could just what you could just know is that e power I theta expansion is nothing but cos theta plus I sin theta. Okay, so you could just Google this later. Okay, you'll find tons of material on this. Okay. So this r equals to square root of a square plus b square, the length of this, and then this cos theta is nothing but what? A by square root of a square plus b square, right? Cos theta. Okay. This length by this length, right? So it's going to be a by square root of a square plus b square plus I times sin theta. Sin theta is going to be b by square root of a square plus b square, right? B by square root of a square plus b square. Okay. So which is again going to give you what? A square root of a square plus b square is going to get cancelled out. So it's going to give you a plus ib. Okay. So basically r e power I theta is same as a plus ib. Okay. It is just representing it in a using the angle and then the length of the complex number. Okay. Clear? So now we'll talk about other important concept, which is going to be conjugate. Okay, the conjugate of this complex number, right? A comma b, it's going to be a comma minus b. It's going to be a comma minus b, and this is going to make an angle theta, but then it's not exactly theta. I mean, the modulus is going to be theta, but then it's minus theta. Okay, all right. The angle with which it makes with the real axis is going to be minus theta. Okay. So the conjugate of a plus ib, the complex conjugate of a plus ib, it is nothing but a minus ib. Okay, a minus ib or a comma minus b. Okay, if you just representing it in terms of this point. Okay, and in terms of r and theta, it's going to be r e power minus. Okay, r e power minus I theta. Okay, or you could just write it this way: r equal plus of I of minus I theta. Okay, r e power I of minus theta. Okay, so both the same. So this is going to be the complex conjugate of a plus ib. Okay, a plus ib conjugate is a minus ib. In other words, it's r e power minus I theta. Okay. So basically, since you know that the bond is a comma minus b, right? The length is going to be same. The length is again going to be equal to a square plus b square. Okay. Only the sign of this imaginary part is changing. Okay. Only the sign of this imaginary part will change, and the complex and the conjugate of a minus ib is going to be a plus ib. Okay. Just like complex, the conjugate of a plus ib is a minus ib. Just like the conjugate of a plus ib is a minus ib, the conjugate of a minus ib is a plus ib. Okay, just give me a moment. Okay, just 1 second. All right, so yeah, so this part is clear, right? And you know the complex number and then the conjugate of it, is that clear? Until now, is this clear?
Yes, sir.
Okay.
Yes, sir.
Yeah, okay. So now what we look at is just the basic operation of the complex number. The addition of the two complex number, it's going to be same, just like you do with the normal numbers. Okay, a plus ib plus of c plus id, it's going to give you a plus c plus of this b plus c. Okay, you just consider this as this new number where the complex, sorry, where the real part is a plus c and then the complex part is b plus d. Okay, so the multiplication of it, even this you could do just like you multiply the normal numbers, but since you have this I, okay, so you'll have this I square, right? Okay, so you'll have this AC plus of I square BD. Okay, I square is, since we know I is equal to square root of minus 1. Okay, the I square is going to be the I square is going to be equal to minus 1, right? Okay,
Yes, sir.
so you could just, so that I square it's going to be equal to minus 1, so that's why it's going to give me AC minus BD plus of BC plus AD, it's a common. Okay, so basically you can just do it in the same way. Okay, just like you do the normal multiplication, you could just do it in the same way. Okay, the multiplication of two complex numbers. Just remember that I equals to square root of minus 1. So wherever you get this I square, you just replace that with square root of minus 1. Okay, I square is going to be equals to minus 1. And then this one, okay, so just like you have a vector in the real space, right? So you can have a complex vector where this complex vector is going to be equals to, it can contain this complex numbers. Okay, so what we have over here is we have this C1, C2, C3, C4. Okay, where suppose let's say this is a vector. Okay, so the C1, C2, C3, C4, they all can be the complex numbers. So each one of this, it can be from A plus IB. Okay, so this if you consider like A1 plus IB1, this will be equal to A2 plus IB2. Okay, this is going to be equal to A3 plus IB3. Okay, so basically instead of having just a real part, right, you can have the imaginary part too. So that will be the complex vector. So linear combination of a complex vector, you could just do just like we have done for the real vectors. But what is to happen there is, in the, for suppose let's say like this is x1. Okay, this is x1. X1 is this vector. So the linear combination, it's going to be equal to capital C. Let's think of it like capital C, C2 x2 plus C3 x3 plus and so on. Okay. Suppose we have like n vectors. Okay. So the linear combination of those n vectors, it's going to have this form C1 x1 plus C2 x2 plus C3 x3 and so on Cn x1. So here previously in the
Hello, sir. Are you there? Sir, are you
Hello,
there?
sir.
Hello.
hello, can you hear me?
Very low voice, sir. Very low.
You can hear me now?
No, it's still very low.
Still very low. Okay. There's a problem with my network. Let me change my network. Now is it better?
Yes, sir. Slightly better.
Okay.
Yes, it's
Yeah,
better
much
now.
better. Much better now, sir.
Okay, great. So now we'll continue. Where did you lose me?
That linear combination we were talking about.
Yeah, okay. So in this linear combination of the complex vectors, right? So here this x1, x2, they are the vectors, okay?
Please project your screen, sir.
Okay, yeah.
The page is not visible.
Sorry. Yeah. So these going to be the complex vectors, okay? These are x1, x2, x3, and so on the xn, right? These are complex vectors, okay? And then the c1, c2, c3, cn, they are going to be complex numbers, okay? So the difference with the real numbers, I mean the real vectors linear combination, and then this complex vectors linear combination is that their x1, x2, x3, and so on xn, they are the real vectors, and even the c1, c2, c3, the constants, they are also real numbers. But here this can be complex vectors, and this will be the complex numbers. Okay, all right. So that is
Sir,
the yeah,
great, very good. Yeah, C is equals to A plus IB, right? All the C means
right. They are of the form a plus ab. Yes.
and we'll
No,
be integrating the real portion one side and then the imaginary another, right?
No, it's they're combinedly same, right? They're combinedly one number. Yeah. So basically you have the real value and then the imaginary value. You have both.
So, for the C1 x1 plus C2 x2.
Yeah, yeah. So basically, for example, let's say you're going to do this, okay? You're going to do linear combination of two vectors, where the first vector is 1 9, okay? And then the second vector is, say, like -1 I, okay? And then let's say like the C1 the constant for this vector, let that be like 1 plus I, okay? And this, let it be 1 minus I. Okay, so what will this linear combination be? It's going to be 1 plus I into 1, which is going to be 1 plus I. Okay, and then this 1 plus I into I, it's going to be equals to I plus I square, which is going to be -1 plus I. Okay, -1 plus I plus of this 1 minus I into -1, it's going to be -1 plus I, and this 1 minus I into I, it's going to be minus I square plus I. Minus I square is going to be 1, so it's going to be 1 plus I. Okay, so the linear combination of this, it's going to be equals to 1 plus I minus 1 plus I, so it's going to be 2I minus 1 plus I, and 1 plus I, it's going to be again 2I. Okay. Yeah, so
Sir, this C can be both real and complex, right?
yeah. So I just taken one example. Okay, it can be real or complex. So if now of the form A plus IB, right? When this B is equal 0, it will become a real number, right?
Yes, sir. Yes.
Okay. All right. So now the next important topic is this inner product or length. Okay. So when you talk about length of a vector, okay, the length of a vector in the real vector case, what do? You just do it like x transpose x, right? This is going to give you the length. But then if you do the same thing, if you do the same thing with respect to complex vector, okay, it might not give you the length. For example, if you do for this 1I, okay, 1I, if you do it, it's going to be what, 1I multiplied by 1I, right? So it's going to give you 1 square plus I square. 1 square plus I square is going to be equal to 0, because I square is -1. So it's going to give you 0. Okay, but that's not the actual length, right? So but actually one I it does have a length. It does have a length of square root 2. So here what we should be doing is, instead of doing x transpose x, so here the length is going to be x conjugate transpose multiplied by x. Okay, the norm of a vector, the norm of a complex vector, it's going to be x conjugate transpose x. Okay, so similarly, if you're talking about any two vectors, x and y, any two complex vectors, I mean, the x dot y, it's going to be equals to x conjugate transpose y. Okay, or x transpose conjugate y. Okay, both the same. So this is going to be dot product of two complex vectors. All right. So that is one important part. Okay, and then these are
Sir, so can we calculate the length of 1 and I, a vector 1 and I? Can we calculate the
if
length
you
of
do
that?
it this way, right? If you do it x conjugate transpose y, I mean x conjugate transpose multiplied by x, then it's going to be what? The conjugate of 1 and I is what?
1 minus I.
Yeah, 1 minus I multiplied by 1I, it's going to give you 1 square minus I square, which is going to be equal to 2. Okay. So the norm is going to be equal to, I mean, the length of the vector is going to be equal to square root 2. Okay.
No, it is 2 or square. Yeah, square root 2. Yes, square
Yeah,
root
it's
2.
going to be square root, because this is square of the length, right?
Yes, got it.
Okay. Others are able to follow. I hope you are able to follow.
Yes, sir. Clear. Clear.
So x dot y, it's going to x dot y is nothing but this y dot x conjugate. So like in the real vector case, what is to happen is x dot y is nothing but y dot x for real vectors. Okay. But for the complex vector, that's not the case. Okay, x dot y is not equals to y dot x. Okay? X dot y is going to be equals to conjugate of y dot x. Okay? Because x dot y is what? X conjugate transpose multiplied by y, right? Okay, so which is going to be x1 trans x1 conjugate multiplied by y1 plus x2 conjugate multiplied by y2 plus x3 conjugate multiplied by y3 plus and so on. Okay, I mean x conjugate transpose y is going to be equal to this, right? Okay, but what about y dot x? Y dot x, it's going to be the opposite, right? It's going to be y1 conjugate multiplied by x1 plus y2 conjugate multiplied by x2 plus y3 conjugate multiplied by x3 plus and so on, right? So we know that what about the conjugate of this? So this is y dot x is going to be this one. What about y dot x conjugate? Y dot x conjugate, it's going to be equals to y1 conjugate, it's going to be equals to y1, okay, and then multiplied by x1. So this y2 conjugate, it's going to be equals to y2 and then multiplied by x2 conjugate plus y3 multiplied by x3 conjugate plus and so on. Okay, so these three are same. Okay, these two are same. So basically, x conjugate transpose y or x dot y is equals to y dot x conjugate. Okay, so in the real vectors case, what is to happen is the conjugate is nothing but the actual number. Okay, the conjugate of real number is going to be the same number, right? Because for a real number, okay, b part is anyway 0. So a minus ib is going to be same as a plus ib since b equals 0. Since b equals 0, a plus ib is going to be same as a minus ib. That is the reason x dot y is going to be equals to y dot x for real vectors. Okay, but for the complex vectors, x dot y is not going to be equals to y dot x. Okay? You can just take an example. And then do this also. Okay. So that is one important part.
So
And
we can think of complex case to be applicable in real case also, and just because conjugate doesn't affect the real number, so the uh, x that the complex case, that conjugate can be omitted for the real case.
yeah. Since we do not even have the imaginary part, we can just omit the conjugate. Okay, because conjugate is going to be same number. Okay, same value. This we could just do directly. X dot cy it's going to be equal to what? X conjugate transpose multiplied by cy. Since c is a constant, right? I mean, even though it's a complex number, it's a constant. So this is going to be equal to x conjugate c times x conjugate transpose y, which is going to be equal to c times x dot y. Okay. Similarly, if we do it cx dot y, okay, then it's going to be equal to cx whole transpose cx conjugate whole transpose of multiplied by y, which is going to give you, okay, c conjugate x conjugate transpose, okay, multiplied by y. Okay. I haven't applied transpose for this because transpose of a single number, it's going to be same number. Okay. So this is going to be equal to c conjugate multiplied by x dot y. Since x conjugate transpose multiplied by y is x dot y, right? So cx dot y, it's going to be equal to c conjugate of x dot y. Okay, and x dot cy, it's going to be equal to c of x dot y. But for suppose, let's say instead of c is a real number. Okay, if c is a real number, both are going to be same because c is equal to c conjugate. Okay, clear? But generally, since c might not be a real number, it could be generally since it can be any complex number. Cx dot y, we will write it as c conjugate multiplied by x dot y. Is this clear? Abhi tak clear? Hello.
Sir, it will be better if you take some examples.
Okay. For example, let's say like x is equals to, okay, we'll take the same example 1 9, and then y is equals to 1 plus I and then 1 minus I. Okay. This is x and this is y. Okay. And then let's take c is equals to 1 plus I. Okay. So x dot cy, generally what is this x dot y? X dot y is going to be equals to 1 into 1 plus I. Yeah, 1 into 1 plus I, which is going to be 1 plus I. This I value we need to do the conjugate. So it's going to be equals to minus I multiplied by 1 minus I. Okay. I haven't written the steps here. Okay, I have directly written it. I hope this is okay. Hope you are able to follow. This is going to be equals to 1 plus I minus I plus I square. It's going to be plus I square is going to be minus 1. So this is going to be equal to 0. Okay, let's not take this example then. We'll do this. We'll take it as 1 plus I. Okay.
Sir, that will be plus 1, sir. Towards that, it will be plus 1, na?
What? Minus I multiplied by minus I, it's going to be plus I square, right? Plus I
So,
square.
no, in bracket it is 1 minus I, na? In bracket it is 1 minus I, right?
Yeah, actually it's
Okay,
1
so
minus I. What about minus I multiplied by
minus
minus I? It's going to be
minus
plus I
I square means plus I, na, sir? So plus 1, na?
No. Minus I square is plus 1, but we are multiplying minus I with minus I, right? Minus I multiplied by minus I, it's going to give you plus I square. And then plus I square is going to be equal to minus 1.
Yes, okay, yeah.
Okay. For example, let's say like instead of taking this as 1 plus I and then instead of taking this as 1 minus I, let's say like I take it as 1 plus I. So here what's going to happen is it's going to be 1 plus I plus 1 plus I minus I multiplied by 1 plus I. Okay. So now it's going to be equals to 1 plus I minus I square. Okay. So it's going to be equal to 2. Alright. It's going to be equal to 2. But for suppose, okay, this is the value of x dot y, right? Dot y minus I. Check this. X is equals to 1 I. So x conjugate transpose is going to be equals to 1 minus I. Y is equals to 1 plus I. So x conjugate transpose multiplied by y is going to be equals to 1 minus I multiplied by 1 plus I, which is going to give you 1 plus I minus I square. Yeah, which is going to give you 2. Okay. I don't think it will be the appropriate example, but okay, let's try this. Okay. So now, right, this is equals to x dot y is equals to 2. Okay. What about x dot cy? Okay. Where c is equals to 1 minus I. Okay. Let's try this. Okay. Where c is equals to 1 minus I. Now it's going to be equals to what? It's going to be equals to x conjugate transpose is going to be same. It's going to be equals to 1 minus I multiplied by c multiplied by y is what? Y is equals to 1 plus I, right? Multiplied by 1 minus I. It's going to be 1 square minus I square. Okay, 1 square minus I square, which is going to be equals to 2. Okay. So cy is going to be equals to 2. Okay. Is this clear? 1 minus I multiplied by 1 plus I, it's going to give you 1 square minus I square. Minus I square is going to be equals to 1. So 1 minus I multiplied by 1 plus I is equal to 2. Similarly, 1 minus I multiplied by 1 plus I, even in this part is also equal to 2. So x dot cy is going to be equals to 2 minus 2i. Okay. So this 2 minus 2i, right? What is this? It is nothing but C multiplied by X dot Y, right? Where C is equals to 1 minus I multiplied by X dot Y is what? 2. Okay. So this is what we have seen. X dot Cy is going to be equal to C multiplied by X dot Y. Okay. X dot Cy is equal to C multiplied by X dot Y, which is what we have seen. Okay. But what about Cx dot Y? Okay. Cx dot Y, let's do the Cx. X is equals to 1i, right? X is equals to 1i, so Cx is going to be equals to this one, which is going to be 1 minus I minus I square, which is going to give you 1 plus I. Okay. Minus I square is going to be equals to 1, and then multiply 1 multiplied by is I, so it's going to give you 1 plus I. Cx is equals to 1 minus I, 1 plus I. Now what about Cx dot y? It's going to be equals to Cx conjugate transpose multiplied by y, right? So which is going to give you the conjugate transpose of this 1 minus I, 1 plus I is equals to 1 plus I, 1 minus I. Okay. So you just change this to 1 plus I and this to 1 minus I. Okay. Multiplied by what about the y? Y is equals to 1 plus I, 1 plus I, right? Y is equals to 1 plus I, 1 plus I, which is going to give you 1 plus I multiplied by 1 plus I is going to be equals to 1 square plus I square plus 2i. 1 square plus I square is going to be equal to 0 because I square is equals to minus 1. So this is going to be equals to 2i. Okay. And then this 1 minus I multiplied by 1 plus I, what is that? 1 minus I multiplied by 1 plus I, it's going to be equals to 1 square minus I square, right? Which is going to be what? 1 square minus I square is 2, right? So this is equal to 2 into 1 plus I. Okay. What is this 1 plus I? You have C is equals to 1 minus I, right? So C conjugate will be equals to 1 plus I, right? So basically Cx dot y is equals to C conjugate multiplied by 2. So which is nothing but C conjugate multiplied by X dot y, because X dot y is 2. Okay. So here we could see that X dot Cy is equal to C multiplied by X dot y, whereas Cx dot y is equals to C conjugate multiplied by X dot y. Okay. Is this clear with the example? Hello.
Yes, sir, it is clear. But one question, sir, where will we be using this complex number?
Where we will use this?
Complex number.
Hello. Where you will use this? That's your question, is it?
Yes, sir. In machine learning, where will we?
So whenever you know this X dot y, okay, and then if they ask you to find this X dot of Cy, right? You can just directly use the X dot y value to get this overall value. Okay, you need not compute the overall thing again. Okay, so it just helps you in like understanding how this how the C value affects the dot product. Okay, and then it actually helps you in like reducing the steps. Okay, it can help you in like computing in a less time. Okay, that's the only thing. All right. So now, what do we mean by this conjugate transpose? Conjugate transpose is nothing but a conjugate transpose. Okay, so a conjugate transpose that you will call it as conjugate transpose or A star. Okay. So until now we are talking about this X conjugate transpose or Y conjugate transpose, right? So X star is going to be equals to X conjugate transpose, okay, or X transpose conjugate. Okay, both are same. That is what we call as conjugate transpose. Okay? That is just definition or like just a simple way of like calling it. Since you will always be using this A conjugate transpose or X conjugate transpose, okay. Instead of repeatedly writing it, you could just write it like X star, okay, or A star. All right, clear? Okay. So now if you want to find for this A, right? For this A, if you want to find the A star, you could do the conjugate first and then transpose later, or you could do the transpose and then conjugate later. Both are same. Okay. For a real matrix, A star is going to be equal to A transpose because conjugate is going to be the same. Okay.
Yeah.
For the real,
Sir, for a real matrix, do we take conjugate?
yeah, we need not have to take the conjugate. That's why they mentioned A star equals to A transpose.
But
Okay.
for real
Because
matrix, we don't take
real,
conjugate. No, sir. Say for example, a matrix is 2, 3. So what is the conjugate of this?
The conjugate is going to be the same, 2, 3.
Yes.
yes,
The
sir.
conjugate
Because
is going to be the
imaginary
same.
part is zero.
What?
Imaginary part is zero in case of
Yeah,
real
yeah, yeah,
matrix.
yeah, yeah. The imaginary part is 0, so the conjugate is going to be the same.
Yes.
Okay. You can represent all the real numbers as a complex numbers. Okay. So you can kind of consider like real numbers as a subset of the complex numbers. Alright? Clear? Okay. Now this you could directly check. Okay, a star whole star is going to be equals to A. Okay, so since we have done this, okay, for example, we are done for this A, right? We have done the conjugate and then transpose. Okay, if you do the same again, that is if you do the conjugate to this, you'll get this. So if you do the transpose to this, you'll get this, and then if you do the conjugate to this, you'll get back A. So
Sir,
A star, yeah.
so star stands for that. It means that we are taking both conjugate and
Yeah,
transpose,
yeah, yeah,
right?
yeah, yeah, yeah.
Star means that. Okay.
Correct. So if you do A star whole star, then you are going to get back A. So and AB whole star is going to be equal to B star A star. Just like you have for AB transpose equals to B transpose A transpose for the real case. Okay, clear? So now what we have over here is for a Hermitian matrix, A star is going to be equal to A. Just like you have a symmetric matrix, right? You have a s- just like you have a symmetric matrix. Symmetric matrix where A transpose equals to A. This is for the real case. For the complex space, we have something called Hermitian matrix. Okay, where for it to be called as Hermitian matrix, it should be A star is equals to A, which is nothing but A conjugate transpose should be equals to A, or A transpose conjugate should be equals to A, because A conjugate transpose or A transpose conjugate both the same. Okay, this is what we mean by the Hermitian matrix. Okay. Now we look at the second lecture. Until now it's clear. Until now is it clear?
Yes.
Yes, sir.
So now what we have over here is we look at the Hermitian matrices and its properties. Okay. The just like for the real space, right? Where symmetric matrices and the orthogonal matrices are like important. Here also we have a similar matrices. One is Hermitian matrix, okay, and the unitary matrix is similar to the orthogonal matrix. Okay. So now we look at the Hermitian matrix. For a Hermitian matrix, since we know A star is equals to A, okay, the one main important property is all the eigenvalues of a Hermitian matrix are going to be real. Okay. So the proof for that was like mentioned here. Just do it here. So what we have here is we have Ax equals to lambda x, right? Okay, Ax equals to lambda x. This should be there for like, I mean, for lambda to be eigenvalue, this should be satisfied, right? So now what we have over here is, if we do this Ax star, okay, then it's going to give you x star, A star, okay, multiplied by lambda star, x star, okay. So this, if you multiply it with x, okay. So this, if you multiply it with x, what you're going to get is, you're going to get x star a star multiplied by x is going to be equals to lambda star x star. Okay, lambda star is going to be equals to what? It's going to be lambda conjugate, okay, because it does not have any transpose. Multiplied by x, and we know that a star is equals to a. So let us use the property x star a star, in place of a star I am replacing it with a. So it's going to give you x star a multiplied by x is equals to lambda x star x, okay. But ax equals to lambda x, right? Okay, ax equals to lambda x. So x star multiplied by lambda x is going to be equals to lambda conjugate x star x, okay, which is going to give you lambda multiplied by x star x is equals to lambda conjugate multiplied by x star x. Okay. So since this basically means lambda should be equals to lambda conjugate. Okay. This basically means lambda is equals to lambda conjugate. And when will this happen? When will a plus ib will be equals to a minus ib? When this imaginary part is 0, right? When b equals 0, it will happen. And if b equals 0, then that means it's a real number. So basically, if lambda equals to lambda bar or lambda conjugate, then that means lambda is a real number. So basically, all the eigenvalues are going to be the real numbers, okay, for a Hermitian matrix. All right, clear?
Can you please repeat this?
Not is clear.
This a plus ib part. This part.
No, I mean this derivation. I mean
Okay.
ax conjugate equal to lambda conjugate thereafter.
Okay. So what we have over here is, you have ax equals to lambda x, right? Okay, ax equals to lambda x for lambda to be eigenvalue where x is eigenvector, right? So let us do this star, okay, conjugate transpose for both left hand side and right hand side. So it's going to give you ax whole star should be equals to lambda x whole star, right? Which basically implies ax whole star is nothing but what? Ab whole star is going to be b star a star, right? So similarly here it's going to be
A star x star.
No, x star a star.
x star a star,
Okay.
So here also it's going to be equals to what? X star lambda star, okay? Which basically implies lambda star is nothing but, it's going to be, lambda is just a complex number, right? So lambda star will be equals to lambda conjugate, okay? Because the transpose is going to be same. It will do the transpose for a vectors or for a matrices, okay? You cannot do that for numbers. The conjugate of a number, sorry, the transpose of a number, it's going to be the same one. So that is why lambda star is going to be equals to lambda conjugate. So now what we have here is x star a star.
Now, if suppose lambda is a complex number, so we mean to say that lambda star, suppose lambda is a plus ib, so lambda star will be just a minus ib, which is
Yeah.
lambda bar.
Yeah. I mean, lambda star is nothing but lambda bar. I'm saying if lambda is a complex number instead of a vector or a matrix.
So
Yeah.
so we can look upon a complex lambda as a singleton matrix of a complex number.
Correct.
And then understand.
Yeah. So all the scalars, you can consider that as a singleton matrix, right?
Okay.
Yeah. So now if you multiply it by x, it's going to give you x star a star x is equals to x star. Okay, I can take this lambda bar to the left hand side also. So it's going to give you lambda bar multiplied by x star x. So
And we are taking lambda bar to the left of x star just because it is a scalar.
yes,
It
exactly.
is not the dot product.
Yes.
Okay.
So now what we have is a star since A is a Hermitian matrix, a star will be equals to a, right? So this I can write as this way, okay? And ax equals to lambda x. So I will use a property x equals to lambda x. So x star lambda x is equals to lambda conjugate x star x.
Again,
Okay?
we will take the lambda to the left
Yeah,
of x star,
yeah,
and then
yeah.
lambda equal to lambda bar.
Yes, exactly. Okay. Lambda equals to lambda bar, which means that lambda is a real number. Okay, clear?
Yes, thank you.
So now later what we have is we have a Hermitian. If A is a Hermitian matrix, then for a distinct eigen values, we have the eigenvectors to be orthogonal. Okay? Orthogonal means that x dot y is going to be equal to 0. Okay, the dot product will be equal to 0. Okay, so even further we have a proof. Okay, even further we have proof. So here what we have done is, let's say like ax equals to lambda 1 x, and then this ay equals to lambda 2 y. Okay, so lambda 1 and lambda 2 are all distinct. Okay, so x and y are also going to be distinct. I mean, the x vector and y vector are also going to be distinct. So if you consider x dot ay, okay, x dot ay, it's going to be equals to x dot what, lambda 2 y, right? Okay, it's going to be equals to x dot lambda to y. Okay, from our definition, what we have, x dot lambda to y, it will be equals to x dot cy is equals to c multiplied by x dot y, right? So similarly here, x dot of lambda to y, it's going to be equals to lambda 2 multiplied by x dot y. Okay, okay. Now let us look at the other one. Okay, we will look at ax multiplied by this one, ax multiplied by ax multiplied ax dot y. Okay, ax dot y. So ax dot y, it's going to be equals to what, x star a star. Let me just write it in the normal way. Okay, what about the dot product of like two vectors? So it's going to be ax whole star multiplied by y, right, which is going to be equals to x star a star. Okay, x star a star multiplied by y. Now we know that x star is a star is equals to a, right? So this is going to be x star a y. Okay. Yeah, x star a y. Now what we have is, we have this star a y. Now this a y is equals to this lambda 2 y. So this is going to be equals to lambda 2 y. Okay. Ay is equals to lambda 2y, so this is going to be equals to lambda 2. Okay. Now we got the same one. Should not be the case. X dot ay, x dot ay is equals to x dot ay. Yeah, it's okay. Now this instead of a, okay, instead of a, we can replace it with a star. Okay, because a is a Hermitian matrix. X star a star I can write as ax whole star, right? X star a star I can write as ax whole star, and ax whole star I can write as lambda 1 x star. Okay, since ax equals to lambda 1 x, and from this lambda 1 x whole star, it's going to be equals to lambda 1 conjugate multiplied by x star. Okay, lambda 1 x whole star is going to be equals to lambda 1 conjugate multiplied by x star, and lambda 1 conjugate x star y is going to be equals to lambda 1 conjugate multiplied by x dot y, right? Okay. So from this 1 and 2, what we can have is, we can have that lambda 1 conjugate is going to be equals to lambda 1, because for a Hermitian matrix,
We are breaking this lambda 1 x whole conjugate y as x star lambda 1 star y,
yeah,
and
yeah,
then taking the lambda 1 star as a conjugate
yeah,
and taking it outside, and then
right,
x
x
conjugate
star
y
y,
becomes x dot y.
yeah, exactly. So here all the steps are missed, but that's kind of like apparent, because lambda 1 x whole star, as I said, it's going to be equals to lambda 1, okay, lambda 1 conjugate multiplied by x star, okay, and x star y I can write that as x dot y. So the overall value it will be equals to lambda 1 conjugate multiplied by x dot y. And if you compare this x dot ay from first equation we got as lambda to x dot y, and from the second equation we got it as lambda 1 x dot y. So since we know lambda 1 is not equal to lambda 2, the only way these two can be equal is if x dot y is equal to 0. Okay, clear? So since x dot y is equal to 0, we can say that x and y are like orthogonal to each other. Okay, clear? Clear this one? Now since we know that x dot y is equal to 0, which basically means x and y are orthogonal to each other. Okay, so when x and y are orthogonal to each other, we can say that they are like they are linearly independent, right? We have seen that when two vectors dot product is equal to 0, which means that they are like perpendicular to each other, or which basically means they are linearly independent. Okay? And similarly, if you have like n distinct eigenvalues for a Hermitian matrix, then you can have the n independent eigenvectors. Okay, just like you have for lambda 1, lambda 2, you got two independent eigenvectors, right? First, suppose you have n lambda values, n eigenvalues. For those, you are going to have n distinct eigenvectors or n orthogonal eigenvectors. So, which is going to form a basis? Which can help you diagonalize the matrix. Just like you have seen the diagonalization for symmetric matrices, right? You can do the same thing here for Hermitian matrices. Okay, clear? So basically we can do the diagonalization of a Hermitian matrix in this form. Okay, we'll look at this later. I mean, we'll look more on this later in the diagonalization of Hermitian matrices. For now, what we look at is the later one. We'll try to understand the unitary matrices. Okay. For the real world, I mean, for the real space case, what we have is if you have A multiplied by A transpose equals to I, or A transpose A is equals to I, then A is said to be orthogonal, right? A is said to be orthogonal matrix, right? And
Yes, sir.
in an orthogonal matrix, all the vectors, I mean, all the columns are going to be perpendicular to each other. Suppose if A is equals to B1, okay, B1 is the first column, B2 is the second column, B3, B4, and so on, Bn. Okay, so here what we have is we have Bi dot Bj is going to be equal to 0 if I is not equal to 0. So basically, what they're saying is B1 dot B2 is 0, B2 dot B3 is 0, or B1 dot B3 is 0. Similarly, you take any two distinct columns, the dot product of those two columns will be equal to 0. Which basically means they are like perpendicular to each other or orthogonal to each other, right? So, if you have the other important part is the length of each vector or the length of each column, it should be equals to 1. Okay. So this is the orthogonal matrix which we have already seen in the fourth week. Okay. Now for the unitary matrix, as we know, we can't be having just the transpose. Okay. For the complex case, it should be having the conjugate also. So if A conjugate transpose multiplied by A, if it is equals to I, or we'll call it as a unitary matrix. Okay, so that is why instead of writing it as A, I'll write it as U. Okay. I mean, you could write it as A also, but then since we are giving the name as unitary matrix, I'll write that as U. Okay. U conjugate transpose U, if it is equals to I, then U is said to be unitary matrix. Okay. Just like you have for this Bi dot Bj equals 0 for a orthogonal matrix, the same thing you have for this. Okay, sorry. The same thing you have for this unitary matrix. So for a unitary matrix, let's say like a unitary matrix is comprised of columns C1, C2, and so on, Cn. Okay, Ci dot Cj, it's going to be equal to 0. Okay, even here also the dot product is going to be 0. But then since these are like complex vectors, you compute the dot product in a different way. Okay, we know that Ci dot Cj is equals to Ci conjugate transpose multiplied by Cj. Okay, or Ci star multiplied by Cj. Okay, we won't just be doing the transpose, we do the conjugate also because these are like complex vectors. Okay, but this is unitary matrix. It is exactly same as this orthogonal matrix. Okay, so now is this clear? The unitary matrix, the basics, the understanding of it.
Yes, sir.
Okay, so it is exactly same as this orthogonal matrix, but then since it is for those complex space, you'll replace the transpose with respect to star. Okay, because you need to do the conjugate also. And if you're there for this 4 week lectures, right, the live sessions, there I talked about there I talked about 2 important things where orthogonal matrix, it will not change the
So in unitary matrix, each column is having a norm of 1.
correct. Yeah,
And
yeah, it's going to have
yeah,
norm of
and any Cij will be 0 because they are orthonormal.
correct. Yeah, Ci dot Ci, it's going to be equal to 0 because they are like orthonormal. Yeah. Okay. So one other important thing is we have seen for this if A is orthogonal, okay, if A is orthogonal, then what we know is we know that modulus of Ax is going to be equal to modulus of x only. Okay? So basically, the projection of A with x, it's not going to change the length. Okay, it's not going to change the length of the vector. Similarly, okay, similarly for this unitary matrix, the modulus of ux, it's going to be same as the modulus of x. Okay, so basically the length of the vector, the length does not change. Okay, the proof for that is it's like very straightforward. You can take this modulus of ux whole square, which is going to give you ux dot ux. Okay, let's take this modulus of ux whole square. It's going to give you ux dot ux. Okay, this is nothing but ux whole star multiplied by ux, right? And this is going to be equal to x star multiplied by u star u multiplied by x, right? And we know that u star is equal to I. So x multiplied by x, it's going to be equal to, sorry, x star multiplied by x, it's going to be equal to x star x, okay, which is nothing but the norm of x, right? Okay, so basically the length of the vector does not change. And since we know that the length of the vector does not change, we can prove that the absolute value of eigenvalue is 1. Okay. For example, let's say like x is eigenvector, which basically means ux equals to lambda x, right? Ux equals to lambda x. But then we know that the length of this is going to be same as the length of this, okay, which basically means the length of this is going to be equal to length of this one, right? I'm sorry, suffering from cold. So this modulus of, I mean, the length of the vector x, it's going to be equal, it should be equal to the length of the lambda x, right? Which basically means, okay, the length of lambda x, it's going to be equal to the length of lambda multiplied by the length of x, okay, which in turn gives this equals to 1, okay. So basically the length of this lambda is equal to eigenvalue, right? Length of the eigenvalue or absolute value of eigenvalue is equal to 1. Okay. Is that clear?
Yes, sir.
So now what we have over here is we have this eigenvectors, just like for the case of Hermitian matrices. Okay, we have here also the eigenvectors are going to be orthogonal to each other for a distinct eigenvalues. Okay, the eigenvectors are going to be orthogonal to each other, and
In the alternative proof for second property, can you please take a look? Yes.
yeah,
Here, sir, in the third step, sir has written lambda bar x dot x.
yeah.
So is it shouldn't it be lambda bar lambda? Can you please
Lambda bar
take it?
lambda,
Yes.
lambda bar lambda or lambda bar both are going to be same, right?
No, that I understand, but the order in which it is written,
Yeah. The order it's not exactly correct, but then it doesn't matter.
correct. So exact order should be lambda bar lambda, correct?
Yeah.
Okay, thank you.
So now, like even here we know this lambda bar is going to be equals to modulus of lambda. Lambda bar gives the length of this complex number, right? And if that is equals to one, lambda bar is equals to one, which basically means the length of the eigenvalue is equals to one. Okay. I don't know if I have said you this. If I talked about this, where we talked about a plus ib, and then the conjugate is a minus ib, right? And then we talked about r equals to a square plus b square, okay? And this r square, which is going to be the length of this c1, length of the c1 whole square, okay, is equals to c1 dot c2. I mean c1 multiplied by c2. Okay, a plus ib into a minus ib, or c1 multiplied by c1 conjugate, because cb is nothing but c1 conjugate, right? So any complex number multiplied with its conjugate, it will give you the length whole square. Okay. So that is the same thing they have used here. Lambda bar is equals to one, which basically means the length is equals to one. So the next important part is just like for the Hermitian matrices, even here we have for distinct eigenvalues, the eigenvectors are going to be orthogonal. Okay. The proof for that was given here. Could see here x dot y is equals to ux dot uy. Ux dot uy is going to be equals to lambda one x dot multiplied by lambda 2y, which in turn is going to give you lambda 1 conjugate multiplied by lambda 2 of y. Okay. Since these two are equal, lambda 1 conjugate multiplied by lambda 2 minus 1 should be equal to 0, and which will not happen. Okay. When will, if lambda 1 is not equals to lambda 2, then lambda 1 conjugate multiplied by lambda 2 it not be equals to 1. Okay. So basically, this lambda 1 conjugate lambda 2 minus 1, this is not be equals to 1, which means that x dot y should be equal to 0. Okay. So for two distinct eigenvalues, just like for the Hermitian matrices and just like for the orthogonal or the symmetric matrices, the eigenvectors are going to be orthogonal. Okay. Yeah. So later for this diagonalization part, what we can say is for a Hermitian matrix A, we can find a unitary matrix U such that A is equals to U multiplied by this diagonal matrix U star. Okay. Okay. This diagonal matrix I'll call it as this big lambda. Okay. Big lambda multiplied by U star. Okay. So this we can see. I mean, for a Hermitian matrix, there exists a unitary matrix U such that A is equals to U multiplied by diagonal matrix of U star. Okay. This is the same thing which you have seen for this symmetric matrices. If you remember, for the symmetric matrices, what you have seen is we have A is equals to something like
P
let's say
lambda P inverse.
this P lambda P inverse. This is for any matrix. This is for any matrix A. Okay. But if A is symmetric, we'll have this as like P lambda P inverse. Sorry, P transpose. Because if A is symmetric, P is nothing but the eigenvectors, right? Eigenvectors matrix, right? You remember there, how do you found P? P is nothing but the eigenvectors matrix. Okay. So for a symmetric matrix, the eigenvectors are going to be orthogonal to each other, which in turn means the eigenvectors combined they form an orthogonal matrix. Okay. So P inverse is going to be equal to P transpose. Is this clear? Not too much?
Yes, sir.
It's clear, right? See, generally, this is correct, okay? P lambda multiplied by P inverse, this is correct. But then for a special case, for a special case of symmetric matrices, we'll have it in this form. Because P inverse is nothing but P transpose. For a case of symmetric matrices, okay? Similarly, what you have over here is, you have for the summation matrices, where summation matrix is similar to the symmetric matrices. You have this unitary matrix. Okay. You have this unitary matrix where A equals to U lambda U star. Okay. So this we look at it. Actually, for this diagonalization part, just like we have for here while we are trying to prove for the diagonalization of symmetric matrices, what we have proved there is we have seen that for any matrix this holds true. Okay, for any matrix with a distinct eigenvalues this holds true. The first one holds true, but for a symmetric matrix this one will go to true. Okay, the second one will go to true. Here, what we'll try to prove is we'll try to prove the Schro's theorem. Okay, where for any matrix, okay, for any matrix, there exists a unitary matrix such that A equals to U T U star. Here, T is not a diagonal matrix, but it's a upper diagonal matrix. Okay. The proof for that was we will try to discuss the proof. A is equals to U T U star, right? Or in other terms, it should be something like U star AU should be equal to T. Okay, because if you multiply this with U, it's going to be equals to UA. Yeah, if you multiply it with U star, it's going to be equals to U star A equals to U star U.
Yes, sir. Both side of T, it will become identity.
Yeah. Now later U star A, it's going to be equals to T. Okay. So if you could prove that U star A equals to T for any matrix, okay, for any matrix, and then from there onwards you could prove for a symmetric matrix, sorry, for a Hermitian matrix, this upper triangle it will actually become a diagonal matrix. Okay. So we'll try to look at this. For A, right? For A, what we can do is you can find a eigenvalue lambda 1 and then corresponding eigenvector x1. Okay, we can try to find. So from there what we can try to do is, for example, let's say this is this 3 cross 3 matrix. Okay, even this U also should be 3 cross 3, right? So this U should be having three orthogonal vectors. Okay, 3 orthogonal vectors. You know this x1. Using this x1, you try to find out the other 2 orthogonal matrices. Like you can choose like any. Okay, like they won't be like unique. They can be any. Okay, you choose any arbitrary. You will choose any arbitrary eigenvectors. Sorry, not eigenvectors. Just a vectors. Okay, which are orthogonal to x1. Okay, which basically means x1 dot z is equal to 0 and x1 dot y is equal to 0. Okay, clear? Until now it's clear. And also y dot z should also be equal to 0. Okay, so for you'll try to find out
So
lambda.
Here we choose x1 we calculate from lambda 1.
Correct.
And for z and y we choose arbitrarily or how?
So like we should be choosing arbitrarily such that this z and u, they should be perpendicular to x1, and then this z and u also should be perpendicular to each other. For example, let's say x1 is equals to 1, 0, 0. Okay?
Yeah, that I understand. But how do we choose arbitrarily?
Yeah, I'll tell you. So for this x1 dot, for suppose let's say like this x1 equals to 1, 0, 0. Okay. Then here what you can use is you can choose 0,
0,
0.
1, 1. 0, 1, 0, 0,
Yeah,
0, 1. Yes.
yeah. 0, 0, 1. Okay. Similarly, in this way we can find the orthogonal, orthogonal vectors to the x1. Okay. So later, so now that we have this z, u, and v. Okay, sorry. How I use the notations in a different way. Here, think of this. Think of this z as a eigenvector, okay, and u and v are the other two vectors which are like perpendicular to this z1. Okay, so since z1 is a eigenvector, lambda 1 z1 it's going to be equals to az1. Okay, z is the eigenvector. Z is the eigenvector, which basically means now we found a unitary matrix with Z and then U and then V. Okay. So what do you have? U star is equals to I. Okay. Now
No, so if U is a unitary matrix, then norm of Z is also 1.
yeah. Norm of Z is 1.
Okay.
We can find the eigenvector, right? Such that the norm of Z is 1. The eigenvectors are not unique.
Okay.
See, when we talked about eigenvectors, suppose let's say x is eigenvector, then Cx is also going to be the eigenvector for the matrix A. If Ax equals to lambda x, then A into Cx will also be equals to lambda into Cx. Okay. So
Yes.
basically, we can find a eigenvector such that the norm is equals to 1. Okay. So we have here u equals to this zu, right? Suppose now we look at this. What do we need to do? We need to find this u star here, right? Okay. We will do this AU1. We will do this AU. AU, it will be equals to A multiplied by this Z U B, right? Which in turn it's going to give you, this is going to be equals to AZ1 U1 okay, and B, okay. AU1 AB, okay. And this one it's going to be equals to lambda 1 Z1. Okay, since AZ1 it is equals to lambda 1 Z1, I could just replace that with here. Okay. So now what we have is we have AU1 equals to lambda 1 Z1, AU and then AB, right? Now if you multiply this AU1 with U star, okay, U star is going to be equals to Z1 conjugate transpose this all these columns, they'll become rows, and then we'll do this conjugate also. Okay. So now what we have is we have here the first element, it's going to be equals to Z1 conjugate transpose multiplied by lambda 1 Z1, right? Since we know the norm is equals to 1, Z1 transpose multiplied by Z1, it's going to be equals to 1. Okay. So basically the first element is going to be equals to lambda 1. Okay. The first element is going to be equals to lambda 1. Here in this first column, second element, what will be equals to? It will be equals to U conjugate transpose multiplied by lambda 1 Z1, right? Since U and Z1 are perpendicular to each other, this will be equal to 0. I mean, U conjugate transpose multiplied by Z1, that's going to be equal to 0. Okay. So this element is going to be 0. Similarly, the third element is also going to be 0. B conjugate transpose multiplied by lambda 1 Z1, it's going to be equal to 0. Okay. This value need not be 0. Okay. This value need not be 0. So now what we have is we have something of the form lambda 1 Okay, some values, and then 0 0 with this B matrix. Okay, even for the B matrix we repeat the same. Okay. For this B matrix, for the B matrix we will try to find the eigenvalue, and then corresponding
Why
eigenvector we will try to find.
why the upper
Yeah,
triangle elements other than diagonal will not be 0? I mean, we are taking
correct. So let's just look at it. Z1 conjugate transpose, U1 conjugate transpose, V1 conjugate transpose, right? Multiplied by lambda 1 Z1 AU1 AV1, right? So what is going to be this element? This element is going to be this Z1 conjugate transpose multiplied by AU1, okay? This is going to be equals to Z1 conjugate transpose multiplied by AU1, right? This element, okay?
so now,
This is
but
equals to,
Z1 and U1 are orthogonal.
yeah, Z1 and U1 are orthogonal, but Z1 and AU1 they are not orthogonal, right? AU1, okay, we have AU1. Okay. Here A is not a is a matrix. Okay. It's not a constant to take away. It is not a constant. So Z1 transpose multiplied by A1, it need not be the, I mean, basically that need not be equal to 0. Okay, clear?
No, I'm not able to understand.
So see here what happens here what happens is we have this Z1, right? Okay. Z1 conjugate transpose multiplied by lambda 1 Z1, that's going to be equal to lambda 1. Similarly, U1 conjugate transpose multiplied by lambda 1 Z1, that's going to be equal to 0, because you could rewrite this as U1 lambda U1 conjugate transpose multiplied by Z1. Okay, and this is going to be U dot Z1. Okay, U1 dot Z1, which is
Yes,
going to be equal to 0. But
yes.
you cannot write the same for this. Z1 transpose multiplied by AU1, it's not the same. You cannot take this A here.
Okay. Because A is a matrix, not a scalar.
Yeah. Okay. So basically, this need not be 0. This could be 0. Okay, but that
Okay,
need not be
understood.
0. Okay.
Yeah.
Okay. So which basically gives
Sir,
you.
that's zero in case of Hermitian matrix, right?
Yeah. Absolutely.
Yeah.
That will be 0. That will be 0 in case of Hermitian matrix. Okay. Okay. Now what we have is here we have this B matrix. Okay. Even until now we know that these two elements are 0. Okay. We do not know about this. This B matrix it need not be 0. Now what we do is even for the B matrix we'll try to find the eigenvalue, and then we'll try to find a unitary matrix P here. Here in this particular case we found a unitary matrix U1, right? Here we'll try to find a unitary matrix P such that P star BP is equals to lambda 2 lambda 3, okay, 0 this way. Okay, just like you found it in this way, right? We can find it in this way now. Okay, this 3 cross 3 matrix we are reduced it to this form. Now this B we can reduce it to this form. Okay, so I mean basically upper triangle. Now now what we have is we have here U2 star U2 that's going to be equals to I. Similarly, P star P is also going to be equals to I, because U and P are unitary matrices. Okay. So now what we have over here is what we can do is we can do this U1 star U1 star AU1, which is going to be equals to this one. Okay. Okay, we just substituted that multiplied by this P star. Okay, U2 star 1. Okay, this U2 star I could write it as this way 1000 P star, and then this U2 I could write this way 100 and then P. If you multiply these two, it's going to be equals to lambda 1 star 0. I mean star then like that be some values, and then this matrix, right? This 2 cross 2 matrix, it's going to be equals to P star BP. Okay, P star PP. Now we know that P star PP is equal to lambda 2 star 0 lambda 3, right? So I could replace that here, lambda 2 star 0 lambda 3. Okay. So basically this has become a upper triangle matrix. Okay. So no matter for any matrix, right, we could find a unitary matrix such that U star AU is equals to T. Okay, upper triangle matrix. Clear? This part is clear. The Schur's theorem proof. It's a little bit complex, but then that is, I mean, we haven't done it like clearly, but then this holds true. Okay. So now we have this U2 star U1 multiplied by A U1 U2, right? We can take this U2 U1 as this one single unitary matrix. Okay, we can take this U2 U1 as a one single unitary matrix. Okay, which is going to be of this form: U star A is equals to T. Okay. Now what we can say is this is an example for that. But for a specific case of the Hermitian matrix, we can see that the T will actually become a diagonal matrix. Okay, because U star A is equals to T. Okay, and then this T star which will be equals to T star is going to be what? It's going to be the conjugate transpose, right? It's going to be the conjugate transpose of upper triangle, which will become a lower triangle matrix. Okay. So T star will be equals to the conjugate of this overall thing, the conjugate of the conjugate transpose of the overall U star A, which in turn it's going to give you U star A star U. Since A star is equals to A, we can write it as U star AU. U star A is equals to T, okay, which will basically mean T star is equals to T. So the upper triangle matrix is equals to lower triangle matrix. Upper triangle matrix, it will only be equals to the lower triangle matrix when the diagonal elements are when only the diagonal elements are existing and then the remaining are 0. Okay, is this clear?
Yes, sir.
Now in this way we can see that we can see that for a Hermitian matrix, okay, we can always diagonalize it. Okay, and then even those vectors, right? So even those suppose A is a Hermitian matrix. Suppose A is a Hermitian matrix, then this A will be equals to U star this U. Okay, where the columns of this U, they are nothing but the eigenvectors of the A. Okay, it is going to be equals to V1. Okay, or let's say like the eigenvectors are x1, x2. X1, x2, and xn are eigenvectors. The eigenvectors. Then this U1 will be equals to x1, x2, and so on, xn. Okay, and then this diagonal one, it's going to just consist the eigenvalues. Okay, lambda 1, lambda 2, lambda 3. Can simply write it as this way: lambda 1, lambda 2, lambda 3, so on. This will be the okay. So this diagonal matrix, it's going to consist just the eigenvalues, and then this U, it's going to consist the eigenvectors of the Hermitian matrix. Okay, clear?
Could you please repeat this part?
Which part? The later part?
Hermitian, yes.
Okay. For a Hermitian matrix, we have seen that this will be equals to this diagonal matrix, right? Instead of upper triangle matrix, it will be equals to diagonal matrix, correct? And this unitary matrix. I mean, we talked about there exists a unitary matrix such that A is equals to U star lambda U, right? And this specific unitary matrix is nothing but the unitary matrix formed by the eigenvectors of Hermitian matrix. Okay. Suppose we have this ax1 equals to lambda 1 x1, and then ax2 equals to lambda 2 x2. Okay. Then this a will be equals to, write this here, ax1 equals to lambda 1 x1, then ax2 equals to lambda 2 x2, which basically means x1 x2 are eigenvectors. Okay. Lambda 1 comma lambda 2, they are eigenvalues. Okay. Now if this A is a Hermitian matrix, then A will be equals to so on. Lambda 1, lambda 2, so on lambda n. Here is going to be 0, 0 multiplied by x1, x2, and so on, xn. Okay. So basically, this U, right? U is nothing but the matrix formed by the eigenvectors itself. Okay. And then this diagonal matrix is nothing but the diagonal matrix formed by the eigenvalues. Okay. So you can, if you know the eigenvectors and then the eigenvalues, you can diagonalize the Hermitian matrix. Okay. Clear? Is that clear?
Sir, I have a question.
Yes, sir.
Okay, so in lecture it was said that there are matrices which are diagonalizable, but those matrices are not Hermitian. Hello?
Yeah.
So the matrix which is used to diagonalize such matrix, are they unitary?
When you talked about this diagonalizable, right? So they won't be unitary.
Okay.
Here we are talking about orthogonally diagonalizable, okay? Not just diagonalizable, orthogonally diagonalizable.
Okay.
When you
Okay.
orthogonally diagonalizable, that matrix it should be unitary. And that
Okay.
happens for this Hermitian matrix.
Okay. Thank you.
So that's all we have, and then the remaining were just the examples. So we look at this practice, not the practice, but the activity questions. Okay. Statement that the inner product of two complex vectors is always commutative.
False.
X dot y is not equal to y dot x, so it's false. And then the consider vectors x1 belongs to Rn, x2 belongs to Cn. Rn means the real space, and the Cn means this complex space. Which of the following computes the square of the x1 x2? Square of the lengths of x1 x2. X1 transpose x1 and x2 transpose x2, that is okay. X1 transpose x1 and then x2 transpose x2. Here the first one is okay because x1 is a real vector, but then second one is not alright. We should do the conjugate also. So the fourth one is alright. Fourth one is alright because for the complex vector you are doing this conjugate. Okay. Why I'm choosing even the first option is you can do the conjugate. You can do the conjugate for a real vector, but it's going to give you the same vector only. So even if you do x transpose x1 or x1 conjugate transpose x1, it's going to give you the same length for a real vector. Okay. Given a complex matrix A star stands for transpose of conjugate or conjugate transpose. So these are just the basic ones. We already discussed this. I don't think we need to get into this. Which are the following properties are true for the common vectors? Okay. Even this we discussed. Okay, this they just asked for conjugate transpose. This is going to be equals to 1. Okay, 1 minus 2i will be there as the diagonal, and then this is going to be to 1 plus I and 2 plus 3. Yeah, so this one will come. Okay, hope this is okay. We'll go to the second lecture. Hermitian matrix in complex vector space or generalization of symmetric matrix. We looked at it. The Hermitian matrix A star is equals to A, and for symmetric matrix A transpose equals to A. Hermitian matrices are orthogonal and diagonalizable. If the diagonals are distinct, it's true. Yeah. The diagonal elements of Hermitian matrix are real. Diagonal elements. Okay, this we haven't discussed. So when we talked about A star equals to A, right? We're basically talking about A conjugate transpose equals to A, right? Right? And then the diagonal elements, for the diagonal elements, their position will not change, right? For example, let's say other C1, C2, C3, C4, C5, C6, C7, C8, C9. Okay. This, if you do the conjugate transpose, if you do for this, it's going to be equal to C1 conjugate, it's going to be C4 conjugate, this is going to come here and this is going to come here, C2 conjugate, C3 it's going to come here, C7 conjugate, C5 conjugate, C6 and C8 they will be getting exchanged, C8 conjugate, it's going to be C3 conjugate, C6 conjugate, C9 conjugate, okay? So basically these both should be equal, right? So basically C1 conjugate should be equal to C1, C5 conjugate should be equal to C5, and C9 conjugate should be equal to C9. Okay? Which in turn means that the diagonal elements are real. Okay? The diagonal elements of a Hermitian matrix are real. The statement is true for all Hermitian matrices. Okay? Eigenvalues of a Hermitian matrices are always real. Eigenvectors corresponding to the distinct eigenvalues of orthogonal are orthogonal, that's true. All symmetric matrices are Hermitian. Yeah, even that's true. Because the real space is the generalization of the complex space. So yeah, that's true. Now if you look at this, a matrix is unitary if its square matrix has orthogonal columns. This is correct. It should not just be having orthogonal columns, it should have orthonormal. Okay. Because the difference between orthogonal columns and orthonormal columns is, for orthonormal columns the length is equals to 1. Okay. And U star equals to U should be there. Sorry, U star should not be equals to U. U star should be equals to U inverse. U star equals to U, then it becomes Hermitian matrix. You're following me, right? Hello.
Yes, sir.
Okay. The number has reduced. If U is unitary, then which of the following statements are true? If U is unitary, then U star will also be unitary. That's for sure.
All of these.
Yeah, all of this. The eigenvectors correspond to the distinct eigenvalues of a unitary matrix. They are going to be orthogonal. Okay. Orthonormal. Yeah, they are going to be orthogonal. Okay, because we cannot say that the eigenvectors are unique. Okay, we cannot say that. As I told, if x is eigenvector, cx also will be eigenvector. So we cannot say that the length is always equals to 1. That's why option A is incorrect, because the length of the eigenvector, it will always not be equals to 1. Every unitary matrix is a Hermitian matrix. It's false. That need not be true.
False.
So the following is true about eigenvalues of a Hermitian matrix. Mod lambda is equals to 1. We talked about that. Now coming here, for dash matrix A, we can find a matrix such that A equals to B A B star. For a Hermitian matrix, we can find a unitary matrix B such that, as per spectral theorem, any n cross matrix is invariably diagonalizable. Any, yes, this is correct. Any enclosure matrix is entirely diagonalizable. So any upper triangle matrix is entirely diagonalizable.
Sir, any Hermitian matrix is unitarily diagonalizable, no?
What? Any?
Any Hermitian matrix is unitarily diagonalizable.
Yeah, that is correct. Then any upper triangle matrix, okay. Don't we? Yeah, correct. Any matrix is not unitarily diagonalizable, it will be like, yeah, correct. So the third one is correct, yeah.
That's Schur's theorem, I think.
Yeah.
Any n cross n matrix is upper triangularizable.
True, yeah. Specular theorem says that, yeah, unitary matrices, Hermitian matrices unitary diagonalizable, correct. So we'll come for the Schur's theorem. Given a Hermitian matrix A, there exists a unitary matrix U such that D star D equals to U star A. But the Schur's theorem is this one, okay? For any matrix A, there exists a unitary matrix such that A equals to U T U star A. That is going to be the given a. Okay, let's look at this option number 3 and 4. The appears singular given an enclosure matrix, there exists a unitary matrix and an upper triangular matrix T such that T equals to UA U star. Okay. Now what we have? We have this. It should be equals to A equals to U to U star. So T will be equals to UA U star A. So T should be equals to okay, A will be equals to UT U star. So the third option is correct. Okay. Yeah. A will be equals to UT U star. So third option is correct. For any Hermitian matrix, spectral theorem states that D is equals to U star A, where U is a unitary matrix and D is a diagonal matrix with the real entries because for a Hermitian matrix, the eigenvalues are going to be the real. Yeah. Every unitary diagonalizable matrix is a Hermitian matrix. This one, yes, it's true. Every Hermitian matrix is indiagonalizable. Okay. This one, every unitary diagonalizable matrix is a Hermitian matrix. Yeah. This was given as false. Every unitary diagonalizable matrix is a Hermitian matrix. So what they're trying to say is there exists a non-Hermitian matrix for which it can be unitary.
So unitary matrix exists, na? I mean, I asked this question earlier, na, about the diagonalizability of non-Hermitian matrix. So the matrix which is used to diagonalize a non-Hermitian matrix can be unitary, right?
Yeah.
Yes.
That's what it is. I'll just look into this. Okay, I'm not entirely sure on this. Third one. Okay.
Yeah, the converse of Schur's theorem is not true. So this statement is actually the converse of Schur's theorem.
It's a spectral theorem, right?
My bad. Yes, spectral theorem. Theorem.
Yeah. So yeah, I'll look into this. Okay. So this alone I'll let you know. Okay then. So that's all from this. Okay. We do not have time to look at the practice assignment. We look at the practice assignment as well as solve this in the tomorrow session. Okay. So thanks everyone. Okay. It's only 3 of you, but thanks.